Okay, let's go ahead and get started. Just another reminder that there is a midterm coming up in a week. Today's lecture and is going to give you some tools to solve problem 1 on the current homework, and there'll be a similar question about the material in this lecture on the midterm. But that'll be the end of the scope of the midterm. So there will be more material. You know, there will be another lecture next Tuesday. It'll be useful, but it'll be useful in the long run, not useful in the sense of the midterm. Thursday, there will be a review session. Friday in the labs, those will also be review sessions. Wednesday, in the labs on Wednesday, there's actually an open question what we should be doing. So when you go to the labs tomorrow, if there's a particular component of the course material that you would like your TAs to go over again with you the following Wednesday as a lead up to the midterm, please let them know so that we can hopefully design an appropriate lab for you guys to work on that would be the most helpful going into the exam. Because there are always conflicts, and especially in a class this big, there will be a conflict exam. Tentatively, the conflict exam will be Tuesday morning, because then we know that the only thing you have a conflict with is this class, and I hereby excuse you from this class to take the conflict exam. There will be a sign-up form. It will ask for why you need the conflict and what your other conflicts are in case the Tuesday from 10:30 to 12:30 doesn't work, so that we can try, we can do our best to accommodate everybody who needs to take the conflict exam for one of the reasons outlined in the student code. For example, maybe one of, I know there are about half a dozen of you who have registration overrides with another class that meets at exactly the same time, so there may be another exam that happens at exactly the same time. There may be, other things that are happening Monday night, scheduled performances, you have a job, things like that, that the student code allows you to take the conflict for. I do need to say this explicitly. An out-of-town interview is not a reason to miss an exam. If a recruiter tells you we cannot reschedule your interview, it means one of two things. Either one, the company doesn't really want you, or two, the recruiter is lying to your face. Recruiters are paid on commission for every interview they successfully schedule. They will wait. You are Illinois students. They will wait for you. Just tell them, no, I'll come back later when you have, let's reschedule. That's not a reason to take the conflict exam. But once the conflict exam exists, we will let you take it regardless of whether you actually need the conflict, as long as you fill out the form and we have room, and we'll try to, we'll have the sign-up form up by the end of this week, and as long as you register in time, say by Friday, we'll let you know when and where and whether or not you're allowed to take it. I'm already starting to get some requests from DRES for students who need accommodation for whatever reason, may need extra time or some technological aids or something else. Not a problem at all. Formally, you're supposed to communicate that to me in advance. I'm perfectly happy to take Drez's word for it if they send me an exam request. But if I do strongly recommend that if you need additional time, that you schedule the exam to take the exam at Drez on either Monday or Tuesday. But Drez also needs a significant amount of lead time to schedule those exam appointments. So I strongly recommend, if you think that you are going to need any sort of accommodation that would require taking the exam at Drez, that you contact them today or tomorrow to schedule your exam. If you want the accommodations to be handled, not at Drez, but in the regular exam, I really need to have your accommodation letter in my hand by, Tuesday's class at the latest. A week in advance is normally standard. Given the number of students in the class and the number of requests I've gotten so far, I'm pretty sure that there are people who haven't approached me or who haven't talked to Drez yet. It's completely not a problem. We're used to this. We do this every semester. It has, zero effect on anything except for the accommodations that you need. Please come talk to me or send me email if you're not comfortable coming to talk to me in front of the entire room so that we can find some other time to communicate. And one last thing. Start on homework 3 already. Problems 2 and 3 are about the material we talked about on Tuesday. This is probably the most difficult part, the difficult task in this particular section of the course for most students. But it turns out one of the questions in problem 1 is also a little tricky. So you won't, hopefully by the end of the day, today you'll be able to get started. Friday you'll get some practice building up context-free grammars. And so then hopefully that'll give you the tools to do what you need for problem 1. But you really do need to start on this as early as you can to give yourself the most time possible to get it done. Any other administrative questions before I go on to the new material? Cool. Okay. So, today I want to talk about recursion. Now, for the last, 3.5 weeks, pretty much, we've been talking about a class of languages, sets of strings that can be encoded using regular expressions and can be accepted by certain classes of finite state machines. And this is, the class of so-called regular languages. Regular languages, remember language here just means sets. These are built from single strings by one of 3 operations. So one is sequencing. You can put one thing after another. One is branching. I can have this alternative or that alternative. And the last is repetition, which of course I can't spell. All right, so sequencing, this is concatenation. Branching, this is or. Repetition, this is the Kleene star operation. Now, what I'm going to add to this vocabulary of operations that you're allowed to use to build up your set, I'm going to add one very simple thing that turns regular languages now into the broader class of context-free languages. All of the above plus recursion. And So the idea is that a context-free grammar is, a context-free language is a language that has a description that's ultimately just built up from individual strings. And it can use the same kinds of operations that you use to put regular languages together, but in addition, I'm allowed to say, and then I pull a string out of this language over here. And when I'm defining that language over here, I could say, and then I pull a string out of that language over there. And when I'm defining this language over there, I say, and then I pull a string out of that first language that I'm trying to build. So what I'm adding to the vocabulary here, you can think of regular languages as kind of describing the behavior of iterative code when you have sequences of operations and you have branching if statements and case statements, when you have loops. And now I'm adding to that vocabulary, now you're allowed to make function calls. You have scope, right? And in particular, functions are allowed to call themselves, and functions are allowed to call each other. Now, I'd love to joke here that recursion was invented by Ernie Bushmiller in 1936, as shown in this cartoon, but that's not true. Recursion is actually, one of these things that entered the formal mathematical vocabulary roughly in the 1910s, about 100 years ago. But there are reasons to believe that recursion is actually what, there are at least some people, some cognitive scientists and psychologists and anthropologists who believe that recursion is the answer to the question, what sets humans apart from other animals? So, for example, there's this book that came out a few years ago called The Recursive Mind that was written by a psychologist named Michael Carbalis, who basically said, animals have the ability to seem to have the ability to understand some kind of structure. They seem to, some animals have the ability to even learn some structured language, like, okay, Rover, go get your collar. Parrots can be, trained to speak, a few hundred words. Other primates can be trained to speak a few hundred, maybe a few thousand words and create small sentences. But what sets humans apart is that in some sense we can create sentences of unbounded complexity by, that's only limited by our patience, by stringing together relative clauses. So last Sunday when the Super Bowl was playing on my TV, which is subscribed to Netflix, and actually I wasn't watching the TV because I was at a party where I had some cake that was made by one of the guests, who's a baker who's been in business since 1972. Right? You don't have any trouble following these lines of phrase, even if I pop back up and say, oh, at the party nobody was watching the Super Bowl, but we ran out of M&Ms. We can string these things together that the sentences sort of act like nesting dolls. I have a noun and I modify it by a phrase, which is itself has a noun, which is modified by a phrase, which is self-modified by a phrase, and so on. And the argument that Corvallis makes is this is a natural survival mechanism that humans developed as part of their evolution in response to more and more complicated evolutionary pressure back when we were all living out on the savannah. But it sort of naturally evolved from an ability that's already present in animals for sort of finite levels of this. In a sense, what he was saying is that what separates humans apart from animals is that animals are regular and humans are context-free. And there are other anthropologists and so on who find, evidence for recursion in non-linguistic contexts. If you look at textiles, baskets, you see all kinds of complicated patterns going back to, Neolithic examples of these things that suggest that the pattern of mind the recursive thinking process is already there. Now, one strike against this particular theory is that this is a Nature paper, a letter from 2006. Similar recursive behavior has actually been observed in animals. So this paper describes song patterns in starlings that starlings will have, will learn phrases from each other. They're very social animals. They seem to, it's not clear whether it's just mating signals or actual communication, but they have these very, very complicated songs. And they can be analyzed and broken down into phrases. And people noticed that certain phrases acted like open parentheses and other phrases acted like closed parentheses that matched them. And starlings were nesting these things 5, 6, 7 levels deep in the songs. So it's not clear that it's just humans that are context-free. Now, this whole idea of context-free languages, the name came from a linguist named Noam Chomsky, who was interested in human language and who'd originally sort of contemplated the idea that there's a common semantic core to many languages, or perhaps all languages, or perhaps human language in general, and can roughly be described as follows. You have these things called sentences, and this is a very, very, very simplified version of this idea. If things called sentences, a sentence roughly is a noun phrase, the subject, a verb phrase, the verb, and another noun phrase, the object. And a noun phrase, well, it could be just a noun, but it might be preceded by a bunch of, by an adjective, which could itself be a phrase. And an adjective phrase might be like an article, the, a possessive, George's, or another adjective phrase followed by an adjective. So I can say, the big red lumpy couch. The big red lumpy is an adjective phrase there. And you can see already there's recursion. An adjective phrase includes possibly a smaller adjective phrase. And a verb phrase could also have, either just a plain verb, or it could have some adverbs on top of it. And then down at the bottom, there are things like, an adjective means friendly or moist or severed. A noun is dog or homework. Possessive, sort of recursively, might include a noun phrase. The big red lumpy couch's legs fell off, it's that sort of thing. And so this would allow you to provide structure to language, structure to the sentences that we speak. Now, there's an even older version of this that I learned when I was in high school, and apparently there may still be a few people out there who see this, called sentence diagramming, where you draw this sort of, this stem plot. I ate my pencil, right, to indicate, subject, verb, object, adjective, and so on. And these things, these diagrams can get arbitrarily complicated. Linguists sort of threw this out decades ago. And now the models that linguists use to model structure inside language look a lot more like this. Okay. Except that humans aren't actually context-free. We can do things that context-free languages can't. And so the whole linguistic hypothesis here is kind of dead. It's like, nah, it's more complicated than that. Anything involving humans, there's a fair chance that you can listen to the entire 2-hour talk and then go, it's more complicated than that. And you'll be correct, although your response will be completely useless. So what is context-free grammar? What is a context-free language? So I'm going to give you, just start with a very, very simple example, just to show you what these things can look like. Okay, so this is a context-free grammar. It has a couple of different features here. One is that just like regular expressions and deterministic finite automata, it has a finite set of things which refer to the finite set as an alphabet. In this case, the alphabet is the language 0, 1. These are the symbols that make up the strings that this language contains. Right? This is a description, a recursive description of a language. A language is a set of strings. It strings over this alphabet. Okay? It also has, these are sometimes called terminals. Okay. I also have another finite set, which are called the non-terminals. In this case, S, A, B, and C. So I want you to think of the non-terminals as names of functions. There's a main function which invariably is called S for start. And so in this case, what the grammar means is when you call the function S, which is going to write down a string, function S has the option of either just calling function A or calling function B. When you call function A, again, it's going to write down a string. It has two options. One is it can write down a 0 and then call function A. The other is it can write down a 0 and then call function C. Right. B is similar, except you do the recursive call before. C, you again have two options. You can either write down nothing and stop. That's the epsilon. Or you can write down a 0, then recursively call function C, and when it returns, then write down a 1. Okay. So these, the lines here are what are known as production rules. They tend to have the form go from A to some string little omega, where A is one of the non-terminals and little omega is a string that is a mixture of terminals and non-terminals. It's a mixture of write down this symbol and recursively call this function. It can have 0 length, there's that epsilon. It can have much longer length. In this example, I only ever have one non-terminal on the right side of a production, but that's just because it's a simple example. That's not going to be true in general. And then you also have to specify a starting non-terminal, which it just by convention is called S for start. Right? Think of this as main. Okay. So this is a program to write down strings. Now, the program is non-deterministic. I have choices for which strings I can write down because when I enter each of these functions, S, A, B, or C, I have a decision to make. Do I do this or do I do that? And I guess. If you like, I spawn off a parallel execution thread and to execute each possibility. And then I would say that the language generated by one of the non-terminals, this is the set of strings that can be generated by calling this function A. And in general, if I have a context-free grammar, this consists of this list of an input alphabet, a non-terminal alphabet, or in a different set, the set of production rules, and the start state. then the language associated with the grammar is just the list of things that can be generated from the start state. Let me give you, here's my grammar. Now, you'll notice I said at the very beginning, a context-free grammar is something you can get to by gluing together individual strings using either branching or concatenation or repetition or recursion. But the branching is of a very specific type. Namely, when you call the function, you branch to one of several cases, chosen non-deterministically, and that's it. If you want to encode finer levels of branching, you basically have to factor that if statement out into a separate function, or that case statement out into a separate function. Okay? You can do this with arbitrary branching. You can always write it, factor it out into this form. So that's what we're going to do. The other thing I said is unbounded repetition. But I claim actually unbounded repetition is a special case of recursion. Look at the first production rule for A here. What does that do? What does that rule allow me to do? I write down a 0 and then I call A, and I write down a 0 and then I call A, and I write down a 0 and then I call A. Yeah. Well, not an infinite number, because this is recursion, I have to bottom out eventually, but an unbounded number, an arbitrary number. In other words, what this tells me is the language generated by A, I can have any positive number of zeros and then call C. Right? So there's a level at which I can, if I wanted to, I could rewrite this as A goes to 0 plus C. Right? So I have an unbounded repetition of zeros before I call C. All right, so let me maybe do this a little bit more compactly, because normally there's a slightly more compact notation that's used for this. So S, A, B, C. S goes to either A or B. A goes to either 0A or 0C. B goes to either B1 or C1. C goes to either nothing or 0C1. So this bar in the middle here, this is what is often known as Backus-Nauer form, or BNF. This is the name of the notation for the context-free grammar. And I want to point out this bar just means or. It just says I'm encoding all the possible production rules for non-terminal B on one line by having this vertical bar separating alternatives. This means now you know 3 different kinds of notation that mean or. Actually, 4 different notations that mean or. There's the logical notation that's the little v. There's the set theoretic notation that's the little u. There's the regular expression notation that's a plus. And then there's the context-free grammar notation that's the vertical bar. There's also the English one, space OR. Or space OR space, yeah. Different standards are applied in different contexts. Just think of these as like different programming languages have slightly different syntax. Don't worry about the fact that there are 4 different standards, because if you do, you'll create a 5th one and there'll be 5 different standards. Okay. All right, so what kinds of things can you do with this? So let me write down, sort of jump into the middle here and write down a string that might be, when I'm generating this, what I'm going to imagine, the way I want to imagine doing this is I start with the symbol S, and these production rules say, whenever you see a symbol S, you can replace it with either an A or a B. Whenever you see a symbol A, you can replace it with 0A or 0C. And so I'm applying these production rules to grow a string. And in the middle, the string might look like this, where here I've written the terminals in red and the non-terminals in blue. And so I might decide to apply a production rule to this symbol, C, which would lead to the string 000C11BAC, because what I've done is I've expanded the C to 0C1 as I'm allowed to do here. Okay. If eventually I get rid of all the non-terminals and I'm left with some kind of string, then I say that this string is generated by this particular intermediate form, but I would also say that the string was generated if it came eventually from S, and this is just something in the middle. If I can start with S, and by applying these rules until eventually I get rid of all the non-terminals, this string is generated by S, or equivalently, this string is in the language of S. Okay. Now notice there may be many choices for which production rule I've applied. So when I saw this C, I could have expanded it as I did here. I could have instead chosen to expand the C further down the line, and I could have chosen to expand that into 0C1, or I could have chosen to just erase it entirely. I could have chosen this B, and then for that B I had two choices, and so on and so forth. Okay, so there are, for any interesting grammar, an infinite number of strings that I can produce, and for each string that I can generate, there may be many, many different ways to generate the same string. Many different sequences of productions that go from the start symbol S and lead to exactly the same string. All of that is fine. The string is in the language if there is at least one way to produce it using these rules. Okay. So more generally, I would say, if I have a string of the form XAY, I can replace it with the string of the form X omega Y as long as there's a production rule that goes from A to little omega. And in the notes, this is written as a squiggly line. This should be read as produces immediately. And then I can write this is that line with a star on it means that I have a finite sequence of substitutions like this. Okay. All right. Now there's another way that I can think about this grammar that in some ways I think makes life a little bit simpler. Let me take a copy of this grammar and put it over here. Which is, I can think of these as rules not for building strings, but as rules for building trees. So my rules are, if I ever see an S, I can drop a child down below it that's labeled A. If I ever see an S, I can drop a child down below it labeled B. If I see an A, I can have two children labeled 0 and A, or I can have two children labeled 0 and C, and so on. C, I end it, so that's a leaf.
Or I can write the epsilon if I really want to be careful. C, I can get 3 children labeled 0, C, and 1.
And what this allows me to do is grow what's called a parse tree, and then when I read off the leaves, that gives me the string.
So for example, I could take an S, I substitute with an A, and then 0, substitute 0 in A, then substitute 0 in C, then C, I substitute 0, C1, and then again 0, C1, and then this last C goes to an epsilon. And now if I read off the string, I get 0, 0, 0, 0, 1, 1.
Okay. Now, the nice thing about doing things in the form of a parse tree like this is that it kind of takes out the ambiguity of which rule do I apply next. I mean, in this example, there was only ever one non-terminal, but in more complicated examples, if I reach an intermediate state with multiple non-terminals, I could expand on the left or I could expand on the right. All that would show up the same way in the parse tree, just this node has children and that node has children, and there's no sense of ordering. And so it removes some of the ambiguity from how you show that a string belongs to the language. It doesn't remove the ambiguity entirely, because the same string might have multiple parse trees even that lead to the same string. I might show an example of that later. But as long as there is a parse tree where the string shows up as the sequence of labels, then we say that this is a string in the language of the grammar. Okay. So here's a couple of different ways to think about what the notation means. What are we actually encoding here? So what I want to work towards over the next few minutes is, what is this language? Right? This is, well, I just presented this abstract example. It's in this weird notation. It's a little hard to wrap your head around what it means because you're just learning the notation. But with a little bit of thought, we might be able to figure out what language this grammar generates, what it represents, meaning how would I describe it in English? And then in the labs and in the homeworks, we're going to go the other direction. Given something that we've described in English, how do we turn it into a grammar? So I'm sure questions are going to come up. Please ask them. But I want to start by looking at this simpler component of the grammar and just think of this as a grammar by itself. What language is this? What strings can be generated by this grammar? Okay, so clearly every string in this language starts with a 0 and ends with a 1 if it's non-empty. And a little bit of thought would, by induction, think, okay, clearly it's going to be a bunch of zeros followed by a bunch of 1s. So one conjecture is this is just a fancy way of saying 0 star 1 star. Is that right? In the back. Right. It's 0 to the n, 1 to the n. It's not 0 star 1 star, because whenever the grammar, when I'm building up a string by applying this production rule, whenever I write down a 0, I also write down exactly 1, 1. So the number of zeros and the number of 1s are always exactly the same. Okay? So no, this isn't right. What I actually want is 0 to the n, 1 to the n, where n is any non-negative integer. How would I write 0 star 1 star as a context-free grammar? So just a, aside here. How would I write 0 star 1 star? And let's use the non-terminal s for starting this time. Yeah. Okay. So here, notice the difference between these two grammars. Both of them allow me to generate the empty string, but here, the choice of whether to generate a 0 or a 1 is decoupled. I can decide however many zeros I want and independently decide however many ones I want, whereas for the grammar down here in the red box, whenever I have put down a 0, I also must put down a 1. Now, it turns out any regular language can be written down as a context-free grammar. It's actually, I think this is a prototypical example of how you would do it. This pretty much tells you how you would do Kleene closure. Now, there's another way that I could do this, actually. I could write S goes to AB, and then A goes to epsilon or 0A, and B goes to epsilon or 0B. This is how you do concatenation. I just concatenate. I just take, this part and that part are generated by two different functions, and so I just name the two functions and glue the symbols together. The way I do branching is I put that vertical line in saying you could either do this or that. And this is the general strategy for building up, one of those should have been a 1, building up a Kleene closure for language. So any regular language is generated by context-free grammar. It's a context-free language. This language is the prototypical example of a language that is not regular. You can't recognize strings in this language without being able to count something. So when you're generating this string, or when you want to recognize the string, where is the counting happening? Yeah. Right, in the recursion. The depth of your recursion is a counter. Right? So I get to decide how many levels do I recurse. And that will end up being the number of zeros and the number of ones. This is also, something else to keep in mind. When you're dealing with context-free grammars, a language is likely to be context-free if you can figure out a way of recognizing it with exactly one counter, which you can somehow encode as the depth of some recursion stack. If you need 2 counters, it's probably not recursion-free, or it's probably not context-free. So as an example, the language 0 to the n, 1 to the n, 0 to the n is not a context-free language. Because in order to recognize strings in this language, I don't just recurse down and back up. I have to remember how far I recursed in order to match the zeros. Okay? I'm not going to talk about how to prove things are not context-free. There just isn't time. All right. Okay, so this is a reasonable and actually fairly obvious hypothesis for what this language is. How would you prove it? Good guess. Let me try again. Mumble, 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 something in 374. How would you prove it? Good. It's not a fooling set thing, so it's probably going to be induction. And in particular, I need 2 different inductive arguments to show that these 2 languages are the same. Whenever I want to show that 2 sets are equal, the way I do it is to say, given an arbitrary element in the first set, argue that it's in the second. And then given an arbitrary element in the second set, argue that it's in the first. I need to show subset one way, and then I need to show subset the other way. How would you do this? So let me walk through, at least sketch the 2 sides of the proof. One is every string generated by this grammar belongs to this set. If given a string that's generated by this context-free grammar, it actually does belong to this set described on the left. It has the form 0 to the n, 1 to the n for all n.
Okay, so proof. Well, I said for all n, so let n be an arbitrary non-negative integer. Thus, C generates 0 to the n, 1 to the n. Assume, this is the induction hypothesis, C generates 0 to the m, 1 to the m for all m less than n. Now there are two cases. So I want to prove that C generates 0 to the n, 1 to the n. So there are two cases for my arbitrary integer n. Case 1 is n equals 0. In this case, 0 to the n, 1 to the n is equal to epsilon. And sure enough, there's a production rule that says C generates epsilon. The other possibility is that n is greater than 1. So I have this production rule, C goes to 0, C1. And then by the induction hypothesis, that goes to 0, 0 to the n minus 1, 1 to the n minus 1, 1. That's equal to 0 to the n, 1 to the n. Okay. So I'm doing induction on n, because this is a theorem about for all n. Which means I'm not doing induction on the structure of the grammar. I'm not doing induction on the length of the string. I'm doing induction, in this case, on the parameter that actually has the for all written next to it in the theorem. Okay. Similarly, now I have the other lemma that says, for all w generated by this grammar C, w equals 0 to the n, 1 to the n for some n greater than or equal to 0. So previously we said every string of the form 0 to the n, 1 to the n can be generated. And now we need to prove only strings of the form 0 to the n, 1 to the n can be generated. Notice now it's a for all strings in the language, which means now I'm going to be doing induction using the structure of the grammar. Okay? So fix a string w in the language. Thus, w equals 0 to the n, 1 to the n for some n greater than or equal to 0. Assume for all x in the language with x shorter than w, that x equals 0 to the m, 1 to the m for some m greater than or equal to 0. Now there are two cases. All right, so I look at the list of production rules that produce w, and I think about the first rule. Right? If the very first rule is that I apply to generate the first production that generates this. If the first production is C goes to epsilon, that means that the string w is epsilon, because there are no more non-terminals once I've expanded C to the empty string. There are no non-terminals here, so this is my string. And that's, the empty string is equal to 0 to the 0, 1 to the 0. No zeros followed by no ones. Okay? The second possibility is the first rule I applied was C to 0, 1, C, or 0, C1. This implies that w is equal to 0x1 for some x in the language, which by the induction hypothesis implies that w equals 0 0 to the m, 1 to the m, 1 for some non-negative integer m, and that's 0 to the m plus 1, 1 to the m plus 1.
In this case, I'm doing induction on the recursive structure of the grammar. I'm, in effect, doing induction on the parse tree. If the root of the parse tree has an epsilon hanging down, I do one thing. If the root of the parse tree has the other production hanging down, I do the other thing. And my induction hypothesis argues about subtrees of the parse tree. And I'm not doing induction on n, because n isn't for-alled in the statement of the lemma. Yeah, there's a question in the back. No, I'm not, okay, so, the inductive hypothesis, to keep things general, I'm sort of using the most general induction hypothesis that I can. But the actual structure of the argument, I only ever consider like subtrees of the parse tree. And I could have actually written the induction hypothesis that way. Fix W in the language and fix a parse tree for W. Assume that any proper subtrees have the right structure, and then go on from there. Writing the induction in this particular form is okay, provided that there's a couple of nasty things that can happen if you design your grammar badly. So if it's possible for your grammar to get stuck in an infinite loop where you say, oh, I'll expand S to 2 S's and then I'll change the second S to an epsilon, then when you're considering these substrings, they're not actually shorter, and so the induction hypothesis doesn't work. And then you really do have to fall back on the subtree structure. This is a fine distinction that is not going to have any effect on your grade. It will have an effect, perhaps, when you see this stuff again in 421, for those of you who are taking 421 in computer science majors. But mostly, I just want to show you not this as a formalism, which I'm going to ask you to write down, but as a thought process for how to confirm that the grammars that you're designing are actually what you want them to be. There's a question over here. Okay, so this is a good point. So CFGs can be really ugly. So there's a particular form of CFG called Chomsky normal form. Chomsky. Does Chomsky have a P in it or not? I never remember. Chomsky. Oh, I'll just look it up. It's just MS. Okay. There's no P in Chomsky. Okay. Chomsky normal form. So a Chomsky normal form grammar, you might have a production that says the start non-terminal goes to the empty string. This is the only place where the empty string can show up in the grammar. Otherwise, every production looks like this. Either the non-terminal goes directly to a single terminal, not even a string, just one character, or it goes to 2 non-terminals. And this is it. And when you have a grammar in Chomsky normal form, the nice thing about this is your parse trees are always binary trees. Every branch of your parse tree generates a non-empty string, except for the one possibility, the string that you just have an epsilon at the root. You can throw that out. And so when you're applying the production rules, you can always be guaranteed that the substrings that you're arguing about are shorter, and so you can do the usual string induction stuff. This is also useful to put things into this form if you're trying to do things algorithmically, if you're trying to write code to decide whether a string is generated by a grammar. It's much easier to do this when the grammar is in Chomsky normal form. There's a simple dynamic programming algorithm, which is described somewhere in the notes, called CYK parsing, that works when the grammar is in Chomsky normal form, but needs a lot more effort if the grammar is more general. Fortunately, every grammar can be transformed into an equivalent grammar in this form. The transformation algorithm has the same kind of character as every NFA can be transformed into a regular expression or a DFA, except it's much more complicated. And therefore, the most anyone ever needs to know is there is an algorithm. Given a grammar of length n, it produces a Chomsky normal form grammar of length at most n squared in order n squared time. This is, from here on, and any more details is essentially trivia, unless you're really, actually actively studying these sorts of things. So, we're not going to ask you to create grammars in this form, but again, if you're going to be using context-free grammars, it's useful to know that this form exists. And in particular, if you ever find yourself in a situation where you need to prove things sort of generally about context-free grammars, this is the form that you want to assume and that you can assume safely. Okay. So let's go back to the original for non-terminal grammar here. We know what C is. Okay, so we've now figured out that C is, this generates strings of the form 0 to the n, 1 to the n, for all n greater than or equal to 0. Let's see if we can, I'm not going to want to go through this formally, but let's see if at least intuitively we can figure out what the other pieces of the grammar do. So what do you think B generates? Yeah. C1 plus. Okay, good. Now can you say that in English? How would you describe that without referring to the grammar? Okay, so I should maybe point out that stuff I've written over here in red, I consider this to be English, right? It's not in the language of context-free grammars, but it's a isolated, unambiguous description that should make sense to everybody in the room. Okay, good. Now, can you say that more compactly? Just in isolation, how would you describe the strings that B generates? Yeah. Okay. I think we can do a little bit better than that. What do I put on the right side of the bar? N is greater than M. All right, so if I wanted to, I could write this M is equal to N. What does A generate? Yeah. All right. And now, what does S generate? No, well, it's true that one of them is not 0, but S can't generate the string 0, 1. They're not equal. And this is a, The reason why we had to do this alternation, so you're designing something that I want to spit out strings where the number of zeros and the number of ones are not the same. Right at the beginning, I just decide non-deterministically, well, is the number of ones going to be bigger or is the number of zeros going to be bigger? If the number of zeros is going to be bigger, I'm going to branch off to subroutine B. If I want the number of ones to be bigger, I'm going to branch off, to A. If I want the number of ones to be bigger, I'll branch off to B. Yeah? So the question is, do I also need to say m and n are greater than 0? In this case, no, because 0 to the minus 3 isn't well defined. So when I omit things like n is greater than or equal to 0, what I mean is all strings that are well defined of this form with additional conditions. The only reason I wrote the n greater than or equal to 0 before was to emphasize that there are no additional conditions. Right? But if you really wanted to be formal about this, you would write m is greater than or equal to 0, greater than or equal to 0, greater than or equal to 0, and both greater than or equal to 0, or something like that. But this is a picky detail we're not going to worry about. On the other hand, when we ask you to design a context-free grammar that generates all strings of zeros and ones, where the zeros come before the ones, and the number of zeros is different from the number of ones, we want you to write both the stuff on the left, which is the actual grammar, and the stuff on the right, which tells us for each piece of the grammar why it's there, what it means. And it doesn't have to be written in this particular English notation, or sorry, English mathematical notation. You could say at the top, all strings generated by all of these non-terminals live in the language 0 star 1 star. The first one is number of zeros is different from number of ones. The second one is number of zeros is bigger than the number of ones, and so on. Right? But we do need some kind of, some kind of English explanation for what the grammar is trying to do in terms of at least what the non-terminals are. Okay. All right, so let me ask. Let's see if we can actually solve one. This is strings W in, over the language 0, 1, over the alphabet 0, 1, where the number of zeros is equal to the number of ones. This is a context-free language. So we should be able to come up, I claim it's a context-free language, so we should be able to come up with a context-free grammar for it. Notice this is a little bit bigger than the language we saw earlier, where the number of zeros and number of ones were equal, but all of the zeros came first. Any ideas? Yeah. Uh-huh. Sort of. So, I mean, if I can repeat back what you suggested, you might be able to look for pieces that you know are going to show up in any string that somehow you could describe either with a separate grammar or even describe recursively and glue them together with the grammar. That's exactly the right idea. Yeah. Include all the permutations of 0 and 1, how? Okay, so this would be for, okay.
01S or 0S1 or S01 or S10 or 1S0 or 10S. Why? I mean, it's true that every string generated by this grammar has the same number of zeros and ones. It's less obvious that every string with the same number of zeros and ones is generated by this grammar. Right? How would I generate the string 111000111 or sorry 11100000111? It starts with a 1, it ends with a 1, it has ones together. It's not captured by this pattern. So it's not enough just to that I got everything I got has the right pattern. It also means everything with the right pattern has to be incorporated. Yes. Okay, so let me try to repeat. S is goes to A or B, and then okay, and what are A and B? No, but what do they represent? What is the meaning of A and B? What is the block comment above function A that tells you what A does? Well, first of all, does the grammar work? I can generate the string 0. S goes to A goes to 0. 0 does not have the same number of zeros and ones. So something's not right. Yes? Okay. 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 Sorry, this should be 1, 0. And of course, I've written this wrong. That should be a 0. And this goes to A or B. Okay, how would I deal with 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0? Okay, what you're doing is you're trying to, it's like have them nests as they go in. So the first and last things will be different, and the next things in will be different, and the next things in will be different. But that's not generally going to be true. I could start and end with a 1. So 1, 0, 0, 1 would not fall into this grammar. Yeah. S1. Okay. So again, this is the same nesting idea. It's not going to quite get everything, but we're close. Yeah. The first one was incorrect because it didn't include everything that I wanted it to include. No, it didn't get all strings with the number of zeros is equal to the number of ones. Right. The second grammar was incorrect because it generated strings where the number of zeros and the number of ones is different. So the first grammar was not exhaustive, and the second grammar was not exclusive. Okay, I need, remember there's this two-way street. I'll let you in on the secret. Secret is add one production. Okay, now why is this here? And this is the dirty trick that makes this work. If the string has the same number of zeros and ones, then one of two things is true. Either it starts and ends with different symbols, in which case these two productions are fine, or I guess, or it's empty. But the other possibility, if it starts with ones and ends with ones, okay, imagine as you're walking along the string that you keep in your mind the difference between the number of zeros you've seen and the number of ones you've seen. When you see a 1, it goes up. When you see a 0, it goes down. At the end, it has to go to 0. So if it starts with a 1, it goes up. If it ends with a 1, it went up from -1. So I started with a 0 and I went up to 1. And then later I found myself at -1. Somewhere in the middle, it had to equal 0. Break the string there. There's a prefix where the number of zeros and ones are equal, and there's a suffix where the number of zeros and ones are equal. And I can go further and say, actually, I could make this somewhat less ambiguous. By saying here, A is the language of, no, sorry, even this isn't right. A is the language of things where I start and end with different symbols. In fact, I shouldn't have the epsilon there. And S is everything. So I can always find some prefix that starts and ends with different symbols. Take the first place where this delta is equal to 0. Okay? And then everything else will still, the number of ones and the number of zeros will still be equal. Okay, so this is start and end different. And this is number of zeros equal number of ones. Okay. This is also closely related to the following grammar. Anyone want to tell me what this grammar generates? Yeah. Yeah, these are all strings of balanced parentheses. Every open paren is matched by a closed paren. So if you want some mnemonics here, read this symbol as push and that symbol as pop. These are instructions for a stack that leave the stack empty without ever underflowing. Okay. And what I'm doing when I split here is I say, there may be some intermediate point where the stack is empty. Great, just break it there. If there's not some intermediate point where the stack is empty, I have to start with a push and end with a pop. And the thing in the middle is balanced by just ignoring that top thing on the stack. Okay, this is a brief inoculation to these things. We're really not going to be doing very much except for the lab tomorrow and the homework. If you're interested, you'll see more in compilers and programming languages classes and maybe some NLP classes. That's it. Thank you.